Good afternoon, this is Schweitzer. We're going to do a quick little video on introduction to electron configurations, orbital quantum numbers, and comparing them to a Bohr diagram. So if we look at fluorine, for example. Now fluorine, how many electrons are in a Bohr diagram of fluorine? Let's find a periodic table here. So okay, there's fluorine. It's got 9 total electrons. And therefore it's got 7 valence electrons, but so that means that there's 2 in the first energy level and there's 7 in the second energy level. Alright, so let's go ahead and let's sketch this out. We'd have 1, 2, and then there's 7 here, 3, 4, 5, 6, 7, 8, and then 9 total electrons. So this model dominated for a while, but it turns out that as scientists are doing more investigations, they're finding inconsistencies and lots of things going wrong. Hence, the Bohr diagram goes out and the quantum mechanics comes in. And this is much more detailed, and we're really only scratching the surface of quantum mechanics. You could actually take a whole class on quantum theory, and you'd be in college, and 2, you'd be a physics major, not a chemistry major. So in this case, they're trying to describe the locations of and very descriptions of electrons. And to do this, they're going to use what are called 4 quantum numbers. And these guys are what's called the principal. All right, so we have the principal quantum number. Now the principal quantum number is symbolized by a small letter n. I think we've hopefully seen that with Bohr diagrams, and it just measures energy levels. Then we have a little thing inside the energy levels, and this is where the Bohr diagrams are really starting to fail. There are things called orbitals, and they're kind of like little houses in that where electrons are located. Orbitals. Orbital number. And of course, with the energy levels, it's just 1, 2, 3, 4, etc. Well, the orbital numbers have actually letters. And all the letters eventually have correlating numbers that go with them too. But in this case, we have S, P, D, F, and then the next 2 are called magnetic quantum numbers. All right, magnetic quantum number, which is L sub m, and then we have the spin quantum number. All right, we'll leave that quantum off of there. Just say L sub m, and then L sub s. And this is magnetic, and this is a spin. Now, a couple of things about this. Magnetic represents, these are called orbitals, which are kind of like little houses that they live in. Okay, houses. That's a human sort of characteristic. Applied to this, it's not really a house, but it's kind of locations. Magnetic would be suborbitals. Okay, and then how this would be like little rooms in your house. That's really what it comes down to. Spin is actual electron. And we'll talk more about some of these things as we go. So how many quantum numbers does a Bohr diagram really utilize or describe? And really only one, the principal, which is n. Alright, that's it. All the rest of them aren't shown. It's not showing individual suborbitals that electrons are following, or the suborbitals, or anything else. Alright, so with that being said, let's take a little bit closer look at some of these suborbitals. So these suborbitals is all very mathematical, and we're really just scratching the surface of this. Now, an s orbital, you can Google what an s orbital looks like, but really it's just like a sphere. And it's very much mathematical probabilities of locations of electrons. And at that point, again, it just has one room, one suborbital. And it turns out a suborbital can hold a maximum of 2 electrons. A maximum of 2 electrons. It can hold less, But so one suborbital means this guy can hold 2 electrons total, maximum, because 2 electrons per suborbital, per sub. That's kind of important. And then a p orbital, again, the shape's starting to get a little more complicated. It's got lobes, or little like room suborbitals, and the one coming straight out at you in 3 dimensions. So it's got 3 suborbitals, and 2 electrons each would be grand total 6 electrons. Now again, all of this is gathered mathematically and by evidence. Then we have d orbitals, and you can Google the shapes of these, but there's 5 suborbitals for 10 electrons, and then there's 7 suborbitals for 14 electrons. And technically, this is kind of where it exists today in nature, but technically they would be able to go bigger. Okay. Finally, the last thing we have here, or not last, but moving along here, I guess, is how do the electrons fill in? This is a kind of a complicated Bohr diagram, but we know we have these energy levels. Inside energy levels, we have these houses. Well, how do these houses work out? Now, again, it's all based off of energy, okay? And energy controls everything, all right? Now, it doesn't matter what, but it does. So now the model kind of looks like this. And seems complicated at first, but trust me, once you learn the model, it turns very simple. So one, and at first energy level, only has an s orbital. We call it the 1s. Maximum 2 electrons. The second energy level has 2 electrons. Second energy level has an s orbital, 2 orbitals, and a p orbital. So the model basically states that every time you move up an energy level, you gain an additional room. So this is 2 energy levels, which is two orbitals, 2p, 2s2, and 2p6. Now you know that total electrons here, you learned in middle school, okay, is that the first energy level only has 2 electrons total. And the second energy level has 8. Well, there's 6 here and 2 there, that's 8. So this is where we're getting, how many electrons are in each orbital. And of course, most kids know that it's 2, it's 8, and they know it's 18, but they don't really know why it's 18 electrons. Let's see. Third energy level gets an s orbital, it gets a p orbital, and it gets a d orbital. 3d10. 10 plus 6 plus 2 is 18 electrons. Okay, and then the fourth energy level is 4s2, 4p6, 4d10, 4f14. Okay, and you can add all those up for that next one. That'd be 24, 30, 32 electrons. Most people don't know electrons beyond this point. Okay, and there's reasons for that because of how electrons fill up. Okay, now in this case 5s2, 5p6, 5d10, 5f14. I'm going to put a question mark here. You'll see why. 6s2, get a little bit off my numbers, but it'll work out, it's fine. 6s2, 6p6, 6d10. You should be following along with me in your own little off-ball chart. 6f14 and then 2 question marks. And then the next up here is going to be the 7s2, 7p6, 7d10, and I'm just going to start putting question marks. And the reason why this is important is how do electrons fill into an atom, okay? And that might be an important little aspect to this particular chart here, okay? So if electrons filled into an atom based on energy level, then they would just fill up the, all right, if they were going to fill in by energy level, it'd be really simple. They would just, let me make this bigger or not? All right, so if they're going to fill in by energy level, they would just fill all the 1s in first, all the 2s, then all the 3s, and all the 4s, An atom would just keep building around the outside, like this, and it would just get bigger and bigger and bigger around the outside. But it turns out that's not the way the atom builds. It builds by energy, and the energy changes based on how it fills in. So what happens is that the atom fills in with this corner of the table being the lowest energy. And then out here is the highest energy. Okay, so it turns out that a 4F14 is much higher energy, closer here, let's say a 5S2, even though it's the fifth energy level. So the atom fills in. Okay, so let's draw some arrows first. This is the way we do this. This is the order which it's filling. And I'm going to draw a little arrow. Let's give it a color. Okay, and if you have yours, you can follow along. And it looks like it's going to fill in this guy first. This is the 1s2. Okay, so it fills in these two guys right here first. And then the next lowest energy is right here, which is 2s2. And it'd be one of these guys around the outside. Of course, we don't know which one is the 2s2, or so let's just make it, for example, this guy right here. Come on, get back here, buddy. All right, let's just say it's this guy right here, hypothetically. Okay. All right, and then the next lowest one would be the 2p6, which is going to be all of these guys right here. Okay. But it continues on to the 3s2, which is the next thing. And it seems like things are just filling in nicely. Okay, there's our 3s2 located right there. That's fine. Okay, and then it continues on to the 3p6. Now, the sulfur atom only has 1, 2, 3, 4. Okay, and that's those guys right there, which is fine. But then, rather than it's going to fill in the 4s2 next, and then it's going to backfill in the third energy level D's. Okay, and then before it goes to the 4p, 5s in that direction, and then this is this energy line just shows which energy levels are next. And you can see how out here we're really getting to the point where we're really getting highly energetic and coming off the periodic table. We're still on the periodic table here. And then I can just get this along like this. Okay? This is the order which it's filled. Okay? And that's really what we're going to use for doing an electron. It's called an electron configuration, showing the order that it fills and where the electrons actually go. Okay? All right, so in this situation, let's take a moment and try a couple of these. Okay. Now this is a fancy little table here, but it looks something similar to yours. Okay. I don't have this in your chart, but you can use your own chart from the previous page. Okay. This is just pointing the directions this is going. So my first hydrogen only has 1 electron. So this is the best seat in the house right here. And it's going to be just hydrogen 1s1. Helium has 2 electrons. Both atoms will go in this spot here. Once this one's full, it just takes the next best spot. But right now, the 2 spots are full. 1s2. Both electrons go into that best spot. Well, the lithium has 3 electrons. Okay. So now, where do these 3 electrons go? Well, 2 of them go right here. And next one fills this spot. Now you go back to my chart, you'll see that that works just fine. I'm just following. This is my first one. This is my second one. That holds 4, but I don't need 4. I just need 2, 3, 2, and 1. Okay, so let's do that. So hopefully you see how this chart's the same as the thing you have. This is going to be 1s2, 2s1. You should pause the video and try a couple of these as we go along, or just follow along and hopefully you catch on. Beryllium, okay, that's 4 electrons. That s orbital is not full yet, so it's going to be 1s2, 2s2. Now again, this seems really strange. But after a while, you realize that this model is just the same every single time and isn't a big deal. Boron's got 5 valence electrons. Okay, 5 electrons. So it's 1s2, 2s2, 2p. Ooh, okay, and the p's. Let's check it out. So I got 1, 2, 3, 4, 5. Ooh, okay, so just 1 here. All right. So I've just moved from here, did hydrogen, did helium, now I'm doing lithium, beryllium, boron. Now it's in this area here. Okay, move my way across. I'll do oxygen, I'll do fluorine, do a couple other ones, but that's where we are so far. Oxygen. Okay, so I need, in this case, 8 electrons. Now that p orbital right there can hold a maximum of 6 electrons, in case you forgot. The s orbital can hold 2, the p orbital can hold 6, the d orbital can hold 10, the f orbital can hold 14. And that's because this guy's got 1 suborbital, this guy's got 3, this guy's got 5, and this guy's got 7. Okay, so it's going to be 1s2, 2s2, 2p, and I need how many more? I need to get 8, 2p, 4, I believe. Okay, 4, 5, 6, 7, 8 electrons. This guy has just 9, so it's going to be just increment that guy up to 2p5. And F negative means I gained an electron. So rather than have 9, I got 10. So it's going to be 1s2, 2s2, 2p6. It's 10 electrons. Fluorine, neon. So neon, let's find it. Just did fluorine, we did fluoride, now we got neon. But you notice neon also has 10 electrons. So if I were to do that one, you'd be surprised. It looks the same as this one does. 1s2, 2s2, 2p6. Also 10 electrons. This has got a fancy term we call isoelectric. And really just means same electrons. Iron. Okay, so let's find iron now. It's getting a little bit farther down. Let's find it. It's got 26 electrons. Okay, that's a lot. All it means is I'm going to work my way through here until I get 26 electrons. This was 10. So I'm just going to build Aufbau. This is called an Aufbau chart. Aufbau. And that in German it breaks down to means to build. Okay, so it's going to be just building on the previous one. So it's going to be the same. 1s2, 2s2, 2p6. That got me to here. Next up is 3s2, 3s2, 3p6, 3p6. So 2, 6. This is 18 electrons, by the way. And then 2 more, 4s2. Backfill. Back the D's. And we need to have 6 of them to get to the 26. 18, 20. Now look at it. It backs up to 3d6. Now in some countries they might put that D right here. And that's fine. It doesn't matter where you put it. We in America tend to list them in order that they fill. Other countries list them by energy level. Okay. Now here's our last example of an ion here. And it shows, okay, what is the for iron 2+? This is just it lost 2 electrons. So this just increments down to a 3d4. Okay, everything else is the same. Okay, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. Hopefully that's okay. A little sloppy. Alright, so that's your general way that you write electron configurations, and they're always kind of the same. One builds off the other one. Okay. Alright, so now let's go from an electron configuration to a Bohr diagram. Okay. So try aluminum by yourself. Aluminum's got 13 electrons. Okay. So it's going to be 1s2, 2s2, 2p6, 3s2, 3p1. Okay. Now, just from the periodic table, you should note that aluminum's got 1, 2, 3 energy levels. Okay. So it's got 13, I think not 13 protons, 13 protons. All right. So 13 protons, 3 energy levels. 1, 2. It's really simple to go from electron configuration to a Bohr diagram. 2, so first energy level, that's this guy right here. Okay, so just put 1, 2. And second energy level's got 6 and 2 is 8. 1, 2, oops, 3, 4, 5, 6, 7, 8. Third energy level's got 3. It doesn't discriminate between S's and P's. 1, 2, and I'll put a 1 here. 3. There we go. And again, I'm just filling this thing, so this won't be on your chart, but just give me a remember how we filled it. Okay, went from 1s2, 2s2, 2p6, 3s2, 3p6, and then we didn't fill this one all the way, 3p1. Okay, those are the ones we just went through filling. This one, this one, this one, this one, and this one here. Now the ion. Okay, so we're talking about this already. Well, atoms want a full shell. Okay, so in this case, aluminum is going to try and lose these out 3 electrons, which is going to be these 3 right here. So it's going to be aluminum plus 3, 1s2, 2s2, 2p6. Now this is going to be isoelectric with what? Okay. It's isoelectric with, well, it's got 10 electrons. That's fine. What else has 10 electrons? Neon does. So aluminum plus 3 is isoelectric with neon. Okay, and it would just look like this. Still 13 protons, so it's still aluminum, but it's only going to have 1, 2 energy levels. A little smaller, a lot smaller. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So now we flip back and forth between these two things. Pretty simple. And give it a try on your own. Get some practice problems coming up. Thank you.